So welcome to the first video for Calc 3. These videos are just little summaries of the things that are inside the notes. So I'm assuming that you've read a little bit through the book, that you've gone through my PowerPoint notes, and then I'm going to talk a little bit and give some examples and use some of the examples that were in the PowerPoint, but I'm not going to go through and read the entire PowerPoint because you already have done that and you don't need me to reread things. So basic definitions of vectors. Vectors have magnitude and direction. So you might draw a vector that looks something like this. And back in high school geometry, maybe that looked to you like a ray, right? It had an initial point and then went on forever in one direction. Well, this is a vector. So this starts at this point and is exactly as long and goes exactly in that direction. And that arrow doesn't indicate that it goes on forever. That arrow actually indicates that that's the end of the vector. So the textbook would probably label it with a bold case V. My pen, I don't think, has a bold case, so I'll just put a V with a little arrow on top. Arrow always goes to the right, doesn't matter which way the vector is going. It just tells us that that V is a vector. Now, if you want to find out how long the vector is, basically what you're doing is you're using the Pythagorean Theorem. So when you put those little bars around, and some books use double bars, some use single bars. I think the book we use for linear algebra actually uses double bars on the side for magnitude. This one uses single bars. So if it's at the origin, the magnitude of the vector is just the component squared, right? Even if you take that vector that I drew before like this, there's a horizontal component that goes this way and a vertical component that goes that way. So if you want to find out how long the vector is, take the one distance plus the other distance, square them, add them together, take the square root. Really what you're doing is you're using the Pythagorean theorem to find out how long that vector is. So instead of walking a certain amount going, let's say, east and a certain amount going north, you could find out what your distance was if you took the shortcut and went northeast instead. So for example, I've got a vector 6, 8. So from the origin, it's 6 units to the right and 8 units up. What is the magnitude of that vector? Well, really what you're doing is you're finding the third side of a triangle, where one leg is 6, the other leg is 8, and then that vector is the third side over there. So the magnitude of that vector is going to be the square root of 6 squared plus 8 squared, which if you recognize this as a Pythagorean triple, you might recognize that this is 36 plus 64, the square root of 100, which is 10. So rather than walking 6 units to the right and 8 units up, you could just take the shortcut and walk 10 units. All right, what if your vector is not at the origin? So I've got a vector that's actually defined by 2 points. Point P is where the vector starts, right, over 4 and up 1, that's point P. Point Q is over 7 and up 6, all right? So there's vector PQ. We assume it goes from P in the direction of Q because that's how it's notated here. What is the magnitude of that vector? Well, I've got a couple of choices as to how I can do this. One thing is I can bring it back to the origin, right? I mean, there is a formula. That formula down the bottom will give you the magnitude of PQ. But what if I bring it back to the origin first? Then I don't have to worry about memorizing a second formula. So how do I do that? Head minus tail. So take the end and subtract the beginning. So I'm going to do that for the x-coordinates. I'm going to do that for the y. So look at my x-coordinates. This ends at 7. It starts at 4. So if it ends at 7 and it started at 4, it moved a net of 3 units to the right. The other component ended at 6 and started at 1. So it moved a net distance of 5 units up. Now find the magnitude of that vector. All right, so 3 squared plus 5 squared gives me the square root of 9 plus 25. Don't forget order of operations. Add them first and then take the square root. My magnitude is the square root of 34. Doesn't simplify to anything. There's no perfect squares I can pull out of it. I'll leave it as an exact value. If you want a decimal approximation, it's going to be something a little bit less than 6, but you can leave it as an exact value also. All right, if you want to use the formula, you could throw it in the formula over here. You could do x2 minus x1, so you could do 7 minus 4 squared, because really this is just a distance formula, 6 minus 1 squared. Add them together, take the square root, and that'll give you exactly the same answer. All right, take a look at these two vectors here. I've got a vector 3, 5 and a vector negative 7, 2, and I want to find the sum of those vectors. The sum of those vectors has a name. It's called the resultant. In other words, the result of adding those two vectors together. So I go over 3, up 5, there's vector u. All right, and then vector v goes 7 to the left and up 2. So there's vector v. Now, the question is, when I add these two vectors, where is the answer going to land? Because the answer is another vector. It's not just a number. Vector u plus vector v, the resultant is another vector. Well, we add vectors component by component. So vector u plus vector v, add the two x coordinates together, and 3 plus -7 is -4. And then add 5 plus 2, and you'll get 7. So u plus v is this vector here, -4, 7. Where is that? Well, -4 up 7, the resultant is actually between the two vectors. All right, so if somebody was pulling a piece of furniture to the right and somebody else was pulling to the left and you had that much force between you, where would that piece of furniture go? It would actually go up and a little bit to the left because it's being pulled more to the left than it is to the right. And both of them are pulling up, so you would combine those. And so the resultant is actually another vector that comes between those two vectors. All right, unit vectors. Unit vectors are vectors that are 1 unit long. What unit is it? Well, it depends what you're measuring. If you're measuring in feet, then it's a foot long. If you're measuring in inches, it's an inch long. Oftentimes, we don't even use units with them. There are standard unit vectors. The unit vector I is 1 unit in the positive x direction. Right? So that's the unit vector that goes this way. J is the unit vector that goes that way. So that means that I can write any vector as a combination of i's and j's. Right? So my vector 3, -2 is 3 in the positive x direction, 2 in the negative y direction, meaning instead of writing it as a set of components, 3, -2, like this, I can write it as what we call a linear combination. So 3 units in the I direction, -2 in the j direction. I can write it as an equation like that. All right, so what does 4i minus 2j look like? I'm going to try to put my work up in the corner here. 4i means 4 in the positive x direction. -2j is 2 in that direction. So that's what the vector looks like. All right, the vertical component is -2. The horizontal component is +4. So if I want the magnitude of that vector, I would take the square root of 4 squared plus -2 squared. And that would let me find the magnitude of vector u. 4 squared is 16. Don't forget, when you square a negative, you get a positive. And so the magnitude of my vector u is the square root of 20. If I want, I can simplify this as 2 square root of 5. All right, so those are unit vectors. Suppose then I want a unit vector that is in the same direction as a given vector. Really, what I have to do is reduce it down to a length of a unit, which I can only do if I know how long the vector is. So first thing is, let's find the magnitude of that vector. The magnitude of that vector is going to be the square root of 3 squared plus -2 squared, so square root of 13. And now, take each component in that vector and divide it by the square root of 13. So my unit vector is going to be 3 over the square root of 13 and -2 over the square root of 13. Now, if it makes you uncomfortable to leave your answer like that, you can rationalize that denominator, but I'm not sure it makes it any nicer. I don't know that there's any advantage to writing that first term as 3 square root of 13 over 13, unless there was something that would cancel, right? If I had something that would get rid of, let's say, a common factor of 3 or a common factor of 4, then sure, but it doesn't look like there's anything here. So this thing is a unit long, goes in the same direction. Find vectors of length 5 that are parallel to v. Well, here, can I be cheap for my answer? If I know that this thing here is 1 unit long, and I want something that's 5 units long, why not just take what I have, multiply it by 5? All right, so I can take something that I already know the answer to, and now I've got 15 over root 13 and -10 over root 13. So those are both of length 5, parallel to vector v. All right, so here I got a little jet stream problem, blowing at 45 miles an hour in the direction 60 degrees north of east. All right, so here's east. I want to go north of east. How far north of east? 60 degrees north of east. All right, so I'm going 60 degrees north of east. It's blowing at 45 miles an hour, so vectors can represent other things besides distance, right? In this case, it happens to represent wind speed. I can drop my perpendicular down here, and look at that, I got myself a 30, 60, 90 triangle. 30-degree angle must be up at the top here because the 60 is down the bottom, and that's my right angle. So if you remember, in a 30, 60, 90 triangle, the longest side is opposite the hypotenuse. This must be half of the longest side. So half of 45. And then this side here is short side times the square root of 3. So if I want to write it in terms of i's and j's, what is it doing? It's going 22.5 horizontally, so that's in the I direction. And then it's going 22.5 square root of 3 in the j direction. Right? I could set that up with sines and cosines if I wanted to. Right? I could do sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and then from there, work on it after that. But if I remember 30, 60, 90s and 45, 45, 90s, for this particular problem, I don't have to worry about it. All right, water in a boat. Water's in a river is moving south at 10 miles an hour. Boats traveling due east at 20 miles an hour relative to the shore. In other words, the water is moving, the boat's moving, but the shore is not moving. So I'm going to take my boat speed relative to the shore. Now I want to find the speed and direction of the boat relative to the water. Well, I'm operating in 2 dimensions here. So if the water is moving south, that means the second component is negative. So the water is moving in that direction. All right, the boat's traveling due east, 20 miles an hour relative to the shore. So east is the first component, and it's not moving north or south at all. What I want to find is I want to find the speed of the boat relative to the water. Well, if I add the speed of the boat relative to the water plus the water, I'll end up with the speed of the boat, but that's not what I have. So if you look down the bottom, I switched things around. I made the velocity of the boat relative to the water the boat speed minus the water, right? So the boat is 20, 0. And from that, I want to subtract 0, negative 10. Right? When I do that, I get 20. But now watch the second component. 0 minus a negative 10 is 10. So that's the velocity vector that describes where that boat is moving. But that doesn't answer the question, because the question said find the speed and the direction of the boat. So the speed is just the magnitude of that vector. So the magnitude of that vector is going to be the square root of 20 squared plus 10 squared. So 400 plus 100, square root of 500 miles per hour, whatever that happens to be. Right, you want the direction of the boat. Where is it going? It's going 20 to the right and 10 up. Something like that. I want to find that angle over there. How do I do that? Right triangle trig. So what relates opposite and adjacent? It must be tangent. So if I know that the tan of the angle is 10 over 20, then theta must be the inverse tan of a half. And you can throw that on a calculator. Probably degrees is the better measure here, although most of the times we'll use radians. If I throw this on my calculator, I end up with 26.6 degrees. And then if you want the direction, what is the direction? From going east, I go north that much, so it's north of east. Right? Your original direction goes second, and then from there, tell me how much you turn. So I'm going 26.6 degrees north of east. All right, let's take a look at a couple of quick things from 13.2. 13.2 now gets into 3-dimensional points. When you graph in 3 dimensions, you're actually looking down at the axis, and the z-axis is coming out. So if I were writing this on a board, the z-axis would come out of the board towards the people sitting in the class. You're writing it on a piece of paper, so the z-axis is coming out of the paper. Don't lean over the paper, or the z-axis will hit you right in the nose. If you want to plot the point -2, -3, 5, where are you going? You're going 2 in the negative x direction. That's what this red thing over here is. 2 in the negative x direction goes that way. And then 3 in the negative y direction, and 5 in the positive z direction. So the negative y direction is going down. So you've gone 2 in the x direction, you've gone 3 in the negative y direction, and now you're going to go 5 in the positive z direction. So you're making a point that's not on your piece of paper. It's coming out of the paper and up into that third dimension. Right? How do you find distances between points in space? So this is my beautiful drawing that you can tell here of a rectangular prism. Think about like a tissue box. You're trying to find the diagonal that goes from end to end. So from one corner of the box all the way to the other corner of the box. Now to do that, you're going to need a right triangle. Well, the right triangle is going to be made up of the hypotenuse of the base, right? There's your one side, the height of the object, and then the third side is that right triangle. So the length of A is going to be the hypotenuse of that triangle. B is just going to be the difference between your z's, right? Z2 minus Z1. And then that third side is what we're trying to find. So how do we find A? That's sort of our question first. A is going to be the difference of the x's squared and the difference of the y squared, right? That's the distance formula. Difference of the x's squared plus the difference of the y squared. Well, now, B is just going to be the difference of the z squared. Take the square root, and you're back to just z2 minus z1. All right, so now how do I find C? C squared is a squared plus b squared. Well, you realize what happens is I end up dropping the radical on the top piece. So I end up with an x2 minus x1 squared, a y2 minus y1 squared, and then my third component is just z2 minus z1 squared. Right? If you want just that distance, then take the square root. So that's how you find a three-dimensional distance formula. Difference of the x squared, difference of the y squared, and then really the only thing you're adding is the difference of the z squared, and that's how you find the distance. Here's it written a whole lot nicer than my little drawing over there. Difference of the x squared, difference of the y squared, difference of the z squared. If you want the midpoint of that diagonal, or of any segment, remember for x's and y's, it's just the average of the x's, average of the y's. Well, now if you want it, it's the average of the x's, the y's, and the z's, because now there's three components. All right. This thing over here, there's a section that I talked about spheres, right? You know how to find the equation of a circle. How do you find the equation of a sphere? Well, a sphere now has a three-dimensional center point. So x-coordinate, y-coordinate, z-coordinate. And then other than that, it's almost exactly the same as the equation for a circle. So here, this question says, what is this thing? Well, what if I started grouping things together? So I'm going to group the x squared and the minus 8x together. I'm going to group the y squared and the 14y together. And I'm going to group the z squared and the minus 18z together. And what I'm going to do is I'm going to complete the square 3 times over. So half the middle term and square it. So half of negative 8 is negative 4. Square it and I get 16. So if I add a 16 to this side, I add a 16 to that side. Half of 14 is 7. Square it and I get 49. So add a 49 here and a 49 there. Half of 18 is 9. 9 squared is 81, so add an 81 here and an 81 there. You realize now all three of these pieces can be factored. So this first one is x minus 4 squared, which I know because I set it up so that taking half of negative 8 gives me negative 4. That's the same negative 4. All right, this guy will end up being y plus 7. That third one will end up being z minus 9. Right, each of them squared. Greater than or equal to. Now I got to add these 4 numbers on the other side and see what I get. So I get 50, I get 16, 49, 81, 196. So what is it? First of all, because it's an inequality, it's not going to be a sphere, it's going to be a ball. Where's the center? The center is going to be at positive 4, negative 7, positive 9. the radius is the square root of 196, which is 14. Now, where are these points? These points are not inside, they're outside. So how do I describe the region? It's the region outside a ball with a center of 4, -7, 9, and a radius of 14. So it's not the points on the inside, it's the points on the outside of that sphere. All right, take a look at vectors in R3. So suppose I've got 2 points. I want to find a representation for PQ. So because these points are not centered at the origin, I'm going to have to do some subtraction. So 5 to 1 does what? It moves 4 units to the left. From 11 to 14 moves 3 units to the 3 units up, I should say. And from 12 to 13 moves 1 unit up. All right, so this, to go from P to Q, you'd go 4 units in the negative x direction, 3 in the y direction, 1 in the z direction. All right, the second part of this question asks for the magnitude of PQ. So the magnitude of PQ is just the square root of -4 squared plus 3 squared plus 1 squared. So 16 and 9 is 25 plus 1 is 26. All right, so that's the magnitude of PQ. With those bars on the outside, that means the magnitude. Find 2 unit vectors parallel to PQ. Well, I could take -4 over the square root of 26, right? Because now I want things that are a unit long. 3 over the square root of 26. 1 over the square root of 26. But that's only one. The other one happens when you go in the other direction. So I can put a little plus minus on the outside of here, and now I've taken care of both of them, right? I've gone in the direction of -4, 3, 1, and then I can also go in the direction of 4, -3, -1. All right, 2 vectors of length 4 parallel to PQ, just multiply them all by 4. So 4 times, and I'm going to put my plus minus on the outside here, plus minus 4 times that vector that's up on the top there. All right, and that'll give you 2 vectors of length 4. All right, let's look at the model airplane problem. All right, model airplane's flying due east at 10 miles an hour. So due east at 10 miles an hour means he's going east. He's not going north and south, and he's not going above the ground either. All right, crosswind horizontal blowing south at 5 miles an hour. So south at 5 miles an hour means the second component is -5. All right, because you've got north-south, east-west, and then, east-west, north-south, and then the last one is how far above the ground. All right, the third one is that there is an updraft blowing vertically at 5 miles an hour. So east-west, north-south, that's not affected. 5 going that way. Question is, position vector for the velocity relative to the ground, speed of the plane relative to the ground. So first thing is add the vectors together. So the sum of the vectors is going to be 10, -5, 5. All right, so now if you want the speed is the magnitude of that vector. So the magnitude of that vector is going to be the square root of first term squared, second term squared, third term squared, square root of 150. All right, we can get a decimal approximation if we want. We can simplify that as a radical. So if I want a decimal approximation and see how fast my plane is going, I'll take the square root of 150. I get to 2 decimal places 12.25. All right, one more. Oh, that was just my notes to myself. So I've got a plane flying horizontally due north in calm air, 300 miles an hour. Encounters a horizontal crosswind and a downdraft blowing vertically. What's the speed and direction? So in this case, I'm going to need a little bit of information. So the velocity in calm air, first of all, when you look at this drawing over here, north goes this way, which means you're tilting your axis. So there's north, and there's east. So when we tilt the axes, this is actually our I direction. This is our J direction. And then the K direction is coming out of the graph. Normally, you would think of positives being up here, but the downdraft is negative, so it's down there. Now, the question is, well, all right, the velocity in column error is already given to us, right? That's 300 going north. The crosswind, it said it was going at 45 miles an hour southeast. So this is a combination of I's and J's. It's not just going in one direction. So how do we separate those components? If it's going 40 miles an hour in a direction southeast, that means that there's a 45-degree angle between them. So south, east would look like this. All right. So if this over here is at 40, then each of the sides are going to be 40 divided by the square root of 2, which is, I can simplify this, right? 20 square root of 2 when I get done. Right, 20 square root of 2 which way? 20 square root of 2 in the I direction, and then 20 square root of 2 in the negative J direction, because it's going east, but it's also going south. When I combine these two things together, rather than write 20 square root of 2I minus 20 square root of 2J, I can factor out that 20 square root of 2, and I'm left with I minus J. And so that's why if you look at the picture on the next page, this I stole from the textbook, the crosswind here is listed as 20 square root of 2 I minus J, because part of it is going down and part of it is going in the positive direction. And then the downdraft is there for you too. So if you want the velocity, you got to take the sum of all three parts, right? That's what this equation here says. If you want the velocity, you need the sum of all three parts. So you need the column error part and the crosswind part and the downdraft part. So combine like terms together. So here, I'm going to make a spot for I's, J's, and K's. So there's 300 in the J direction, that's positive. There's 20 square root of 2 in the I direction, that's positive. And there's negative 20 square root of 2 in the J direction. And then the downdraft is negative 30 in the K direction. So if you want to write this velocity as one vector, then you're going to have 20 square root of 2 in the I direction, 300 minus 20 square root of 2 in the J direction, and negative 30 in the K direction. And then if you want the velocity, then just take the magnitude of that vector, right? So first term squared, second term squared, third term squared, add them together and take the square root. So that one I figured I would explain because it's a little bit more complicated, because that crosswind is not going vertically or horizontally. It's going a combination of the two. So you've got to separate those two components. All right, that's the end of 13.1, 13.2.